Well, I would like to welcome you to the fifth lecture in module Deep Learning. And I would appreciate if you could shortly confirm that you can hear my voice and see my slides.
Yes.
Wonderful. Thank you very much. So probably my first question is, how are you doing? How was the lecture last week? Are there any issues, questions, administrative issues, whatever? I think it's the moment probably to say if you are struggling or if certain things do not work as expected. Let me just know, are you getting along with Keras on Google Colab, on Rankolab, whatever you are using? Are there any issues?
One issue of me is that I always have to wait very long. So
For Rankolab, sorry,
yes, no, not on Rankulag, on Colab.
on
So
Google
if I
Colab.
run my script or also for the optimization, I had to wait really long.
Yeah.
So yeah,
Do you have just the usual account, or did you also acquire, uh, I don't know anymore how it is called, Google Colab Pro or
I afforded that one for $10 per month, but
Mhm.
the units they're out of uh, stock already.
Yeah. Well, it's an issue. I've tried to push a little bit the solution regarding Rankolab because potentially there is also GPU. There are also GPU resources. Usually, so far it was working pretty well, or most students reported that Google Colab Pro was working pretty well, but I guess their demand is somehow increasing. Usually it should be enough for this course, but since I have my own GPU workstation, I do not have a Google Colab Pro account. And yeah, I've just tested now all the Jupyter notebooks, and I was lucky to have GPU resources, but sometimes I'm also kicked out and then it's terribly slow. But yeah, um, I mean, the only thing is that you upgrade again, but it's usually not meant to be.
I just want to let you know because that's slowing
Mhm.
me down a lot.
Yeah.
So
Mhm.
also maybe for the exam, if we have a lot of stuff, for example, a learning
Mhm.
schedule, it took me really long also for the optimization
Yeah.
to find a good model.
Mhm. No, thanks very much for the feedback. I think it's still an open issue. You know that there is also Switch Cloud, but this is, as much as I know, I mean, there is a Switch Cloud account, uh, which would be in theory available, but I'm not sure. I mean, I think it's also a little bit tricky because you have to set up all your environment. And just a question, are you aware that there is some Switch Cloud account which you in theory could use for your projects? It's Christian Dolphus. He used to be in charge of this. But yeah, it's an ongoing issue and we need to find a solution. But thanks a lot for I will give a feedback to Patricia Feugli and Andreas Bernberg to probably come up with a more sustainable solution. But it's always
I
the
mean,
Mhm.
all the code you provide and the notes, they're really great, but
Mhm.
I just want to let you know that
Yeah,
for me, that's a bit the problem.
yeah. Thanks a lot. I think that's good to know. Well, are there any other questions, issues, feedback?
One thing from my
Mhm.
side, I wasn't sure in the exercise of the convolutional neural network.
Mhm.
In the second model, I wasn't able to train it.
Mhm.
Also with the solution, I run into an issue there, but might be also a problem from my side.
Yeah. Were you running it on Google Colab, Rancolab, or
On Colab.
on Google Colab? Yeah. I mean, I've been just checking out the notebooks. Again, it's, I mean, in Google Colab, there are constantly upgrades for the version. So there are some functions which are not supported anymore. So what is important, please, just for the session today, just download the latest Google Colab notebooks, because I've done some corrections. I've checked, they should now all be running. It's there are these are minor changes, but still, please just download the latest version from the GitLab repository, because for example, the ending H5, the H5 format is not anymore supported, so you have to replace it with Keras. Then there are some other minor issues. Usually I'm playing a little bit around with Gemini. Sometimes it works pretty well, sometimes a little bit less. If you run into an issue, you always get after the error message, you get the possibility to explain the error. And I would say after 2 or 3 tries, usually it works. And otherwise, if obviously, what you also should consult is always the Keras website. If you run into some issues, just look where the error is, then look up the function, what are the proper settings, and so on.
All right.
But if it doesn't work, please let me know it. I do my best to keep things up to date, but during the semester, it's always a little bit a struggle. That's the reason I'm using the Docker image of Rancolab, which I somehow like, because things work for everyone. And on Google Colab, it's just, I mean, are constantly changes. Good. Well, then let me start. So first of all, I shortly would like to review what we have, or what Simon and you have discussed last week. I got Simon, he always likes very much teaching, especially in person, so he enjoyed a lot. He also likes always the audience, so you. And I hope everything was running smoothly. So let me still shortly discuss what you have seen last week. So we have this convolutional layer, and the core of the convolutional layers are the filters, and these are also the parameters which are going to be trained. So let's have a look at the example of CFAR10 images, where we have an image format of 32 by 32 by 3. So 3 is the depth. And now there is one very important change with respect to the fully connected neural networks. You do not have to reshape or stretch or flatten your images, but you can leave them such as they are. And what you have now are filters which have a depth. So in this case, if the input volume has depth 3, so all the filters need to have the same depth as the input volume. And then you are sliding, or well, that's actually what is the convolution along the image, and carrying out a dot product, adding a bias. So that's basically just an element-wise multiplication between the weights and the pixel values, and then summing up all these products. And this is going to end up in one number per position, and then you are going to slide along the input volume, and this will result in so-called output volumes. Sometimes it's also called feature map. And what is important is you do not use only one filter, but usually you're using a number of filters. So in this case, if you have 6 filters, then the output volume will have depth of 6. And then what is important is the output volume will become the input volume for the next convolutional layer. And in this case, we need a depth of 6 for the filters. So the filters always need to have the same depth as the input volume. And in this case, we have 10 filters, which will result in an output volume with depth of 10. And as you can see, if you do not apply any padding, then what is going to happen is that the spatial size will shrink. So you will always get a slightly smaller spatial size. What is also important, just remember, you always have to apply the rectifier linear unit function, basically just setting all negative values equal to 0 and leaving all the other positive values as they are. So the full convolutional neural network looks as follows. So this is old-fashioned simple one, but here we have an input image, then we have a first convolutional layer with 10 filters. Then we apply activation function, and there is the next convolutional layer. Again, we are going to have we have 10 filters here. Then you have the pooling layer, which is reducing the spatial size of the output volume. And then you continue until you have to still stretch the entire output volume, because you're going to feed in the stretched column vector into this fully connected neural network. And you will end up, if you're applying a softmax function, then you will get probabilities for each class. So in this case, the class car gets the highest probability. And in this case, obviously, you would classify this image as a car, which is correct. Good. Then something which is very important is to understand what are these filters doing. So in the first convolutional layers, they are simply detecting some edges, some blobs, some roundish structure, probably some colors. So these are just some very general patterns which are detected on a rather low scale. If you remember, historically in the beginning, the filter sizes were rather large, 11 in the AlexNet, and then later on they were always getting the spatial size of the filters were decreasing, and the depth of the convolutional neural networks was increasing. So at the end, this is equivalent, as you have discussed last week. And well, if you move down the convolutional neural network, what you start to detect are more larger features like eyes, noses, ears, mouth, and so on. And you always, if you get, for instance, an eye detected at this level, then you get a high activation or a large value for the unit in the corresponding output volume. And that's also something there are ways to visualize what is going on. So for instance, if you're always feeding in images with eyes, so for instance, people, then you will observe that some units get high activation, high values, so you can somehow connect the activation or these units with these mid-level features. And then if you move down very much, then you start to compose, and then you get some high-level features. So in the case, if you have Sarah, then you get a high activation for class Sarah. Good. And what are we going to do today? So today we will first of all have a short lab. I'm not sure whether you were introduced to exercise 4, which I'm always insisting that everyone is doing it because it's about getting your own data set. In my case, I have 2 data sets. One data set is about actors. So these are actors, 8 different actors, 2, 4, 6, 8. Yes, 8 different actors. And basically just downloading a number, I think around 80 images from with Angelina Jolie, then 80 images with Brad Pitt, and so on and so forth. And then you can actually train your convolutional neural network. And now there is going to be one big difference with respect to last week. So today we are going to work with pre-trained convolutional neural network. So we will fine-tune the last layers. That's something I will explain in a minute. So if you just remember last week, you have discussed that these pre-trained neural networks are trained on the ImageNet data set. There are 1,000 image categories, but Angelina Jolie, Brad Pitt, Catherine Deneuve are not part of this data set, of the ImageNet data set. So if you want to apply a pre-trained convolutional neural network to a data set which exhibits some new unseen classes, then you have to fine-tune your pre-trained neural network. So this is going to be the lab. We'll actually start with this part, and then we will generate text. So this is not anymore that interesting because you can generate text nowadays with much more advanced tools. But I think it's a great way, first of all, to introduce text data, and then sequence models also to somehow define what is a language model. So I think it's a great way to understand intuitively what a language model is and what it is doing. I think it's much more difficult to understand if you go directly to a transformer model, which we will do next week. But we will introduce these sequence models or recurrent neural networks by means of text data, which is a rather intuitive task. In the exercises, you will mainly use these sequence models for time series data analysis. And that's where they are still relevant. Obviously, for large language models, you are nowadays not anymore working with sequence models, but still for time series data, these recurrent neural networks or LSTMs, which we will introduce later on, are still highly relevant. Good. So if you want to somehow read or get some more information, so you can move to the CS231 course. I think this course is not the greatest for language modeling or for text data. So it's not bad, but it's not probably not the best one. There are other Stanford courses which are better. Good. So before before we dive into the lab, I shortly would like to explain how transfer learning is working. So first of all, you have seen that there are these pre-trained convolutional neural networks which are available in Keras. So you simply can download the pre-trained VGG16 convolutional network, which was trained probably over weeks, months on the ImageNet data set. And you do not have to do it yourself because anyway, it's going to be too expensive. And you probably won't get the entire ImageNet data set. So what you're going to do is you're going to download this pre-trained convolutional neural network. And then what you have to do is you have to resize your images. Let's say you have downloaded your image data set, then you have to make sure that all the input images have the same size or the same shape. And sometimes you also have to rescale some of the pixel values. So there are, for example, for VGG 16, you have a certain range or pre-processing. And then basically what you can do is you simply can feed in every image of your data set into this pre-trained convolutional neural network. And in theory, what happens is after the convolutional layer, if you flatten the last output volume, then you get a feature vector of length 4096. And in principle, you can start training a model such as a random forest support vector machine, some boosting algorithm with all these feature vectors belonging to your images. And then you can do the image classification in your classifier of choice. So that's one way how to do it. Obviously, you could also continue working with the fully connected network. But yeah, so what is important is to understand that if you have a new images which are not part of the ImageNet data set, then you have to train a classifier which is gonna somehow take into account that now you have new image classes. And what you can do is simply you can extract the feature from the convolutional layers, and then you can use these features in order to train a new network. There is one other way how you can proceed. First of all, you have to somehow think a little bit about your data set. And first of all, you have to decide or to consider whether you have a lot of data or whether you only have a rather small data set. And then you also have to think about whether the images are rather similar to the ImageNet data set. So if it's a new animal category, let's say you're very much into snakes and you have some very exotic snakes you want to classify, well, then you are still probably quite similar to the ImageNet data set because it's still about, there are plenty of animals in the ImageNet data set. However, if you want to classify some technical instruments, or let's say I once supervising a project where someone from SPB was trying to classify parts of trains. So that's probably something which is not part of or which is not at all similar to the ImageNet dataset. So you are dealing with a very different task. And well, so what happens is, let's start with the best case. You have a similar task, so similar to the ImageNet dataset, and you have a lot of data. So that's where that's the case. That's when you are in quite a lucky situation. A lot of data is good, and you have a similar task to the ImageNet data set. Well, what you then usually do is you are training also some of the last convolutional layers. So basically, you are keeping the filters. Always remember that when I say training such a model, that means you are training the filters, the weights in the filters. So what you are usually doing is you are freezing the first convolutional layer. So you are not changing the filter weights of the first convolutional layers, because as we have explained, they are detecting some rather general shapes, like especially in the beginning, you are detecting edges or some very basic patterns. So you do not need to change these filters. But then the last layers may still be relevant for your task. Let's say you want to detect some very specific snake species in the Amazonas. Well, then you may actually consider to retrain or to adapt the last convolutional layers, including also the last fully connected layers. And however, if your task is very different, then you may actually go a little bit deeper and train more convolutional layers, because these layers are already rather custom or targeted to the ImageNet data set. So if you have something very different, then you may also consider training these last layers. And what is important is, if you are doing this, just adapt the learning rate, so make it very small. And yeah. And what is also important is, when you are retraining, just first of all, you need to start with the trained model, and don't start from scratch, obviously. If you have a similar task but little data, then what you're often doing is just you may do what I have described here. So you're only simply extracting the feature vectors. You have VGG16. These are feature vectors of length 4096 units, and then you can train your own classifier, for instance, a boosting algorithm or random forest. And well, if you have little data and very different tasks, then you're in trouble. That's always when things are getting a little bit difficult. So in this case, you may consider that you are extracting the output volumes at different stages, and then you use them to train a new classifier. Good. So now, usually I'm always talking a lot, and that's the part where I realized that you should also work a little bit and get your hands on the problems yourself. So what I suggest is, please just download the latest version of the exercises of convolutional neural networks. So we are still in last week's session. So just take the exercises convolutional neural networks and move to part 3, where it's about creating your own data set. So if you already have done it, then just be patient. I will move on. But those who haven't done it, you need to create your own data set, and that's actually fun. So all you need to do is, what you can do is, first need to close this one. So you can define your own image categories, which you are most interested in. So for instance, here you have the image categories, and in my case, I have 2 data sets, one data set with the actors, and then also one data set with dogs. And let me just, and we are going to work with Google Drive, so we are going to save all the images on Google Drive. Okay, so what happens here is I'm connecting to my Google Drive, and here I have the categories. So in total, I have 1, 2, 3, 4, 5, 6, 7, 8 different categories, like in the case of the actor data set, which I will come to later on. And now what you can do is, you can scrape all these images by means of this very useful package, Beautiful Soup. Then you can download images. So here you can also say how many images you want to download. So all you need to do is please change the name of the categories. So if you're interested into the Simpsons, then just write Bart Simpson. I do not remember anymore. Yeah, Lisa Simpson, and so on and so forth. So just write all the categories you like. If you are very much into traffic, or then you can have some traffic signs or street signs, or just write the categories you're most interested in. And then what happens is Google, this notebook is downloading all the images on Google Drive, and you get a number of images downloaded into the folder. Let me just see here what happens. That's my drive. So basically, if you're gonna have a look at your drive, then then you have brand new images. You can have a look here. And then you can open it here. Now I have for every category. So this is a Bernese mountain dog. Or some more examples. Another one. So that's directly downloaded in your Google Drive folder. Doesn't take too much time usually. Then you get it. Then you can run just this this notebook. Where it's going to happen, it's also going to split your data set into a training data set and the validation data set. So that's also very convenient. And then here the exercise was that you were supposed actually to set up your own convolutional neural network in order to train a model on the training data set, and then to classify it. So if you haven't done it yet, please do it. It was exercise for today, but still you have some time to do it. So here is just a very simple convolutional neural network. And then those who already have done the exercise, they can move to Google Colab. Where is it? That's the other one. So I need to stop this one. And then you move to part 4, which is transfer learning. And then I suggest that you go through this all these steps, but what is actually good is you can apply all this transfer learning directly to the data set you have downloaded on your Google Drive. And so at the end, the goal obviously is you want to figure out, I can also move here, then we see the at the end you will get, okay, that's we cannot see it here. But at the end you can you get a confusion matrix, and then you can also see all the misclassified images. So I think it's not a lot of work, but try to go through this part 4 of the convolutional neural network Jupyter Notebook Part 4 transfer learning. And you basically only have to execute the cells. It's going to do everything automatically. Then what you will probably observe is that it's worth spending some time on cleaning your data. Probably you have downloaded some garbage or some too many objects, too many different objects in your images. So, but still you can run everything. And I think it's a good way to understand how fine-tuning works. And I suggest that you have 30 minutes time, including a break, to get your hands a little bit dirty on convolutional neural network and fine-tuning. Are there any questions? So I suggest do it on Google Colab. That's where I have tested everything. It should work. What's wrong here? I need first to connect. Just try to check whether you have the correct run type. So try to get GPU. Don't do it on CPU if you can choose it. It's run type, or in German Laufzeittyp.
And the exercise is located in the block 4.
Yeah, exactly. So that we are doing some lab or repetition of all the computer vision concepts we have discussed, and then at 1:30 we will slowly move into text data and sequence modeling.
And there are 2 exercises, like one marked with Colab and one marked without Colab.
Exactly. So if you want to run it on Google Colab, which in this case I recommend, do it with the Colab Jupyter Notebook. And again, what you have is, let me just explain again. You have the exercises, convolutional neural network, Google Colab. If you go to part 3 or exercise 3, then you can generate your own data set, which is going to be saved on Google Drive. All you need to do is you need to define the categories, your image classes, and then afterwards you upload the convolutional neural networks Colab. You move to part 4 and you simply execute all the cells. Try also to go through all the text and notebooks to understand how the fine-tuning works.
Thanks.
So I will just grab a coffee, and then in 5 minutes I'm back, and then in case you're experiencing some problems, issues, or if you have some questions regarding fine-tuning, please let me know.
Hi, can I ask a question?
Yeah, of course. Yeah.
I'm having problems with the split folders actually. I'm not sure because it doesn't like find the setup, and I mean I think I'm not sure where it clones when I'm like using it in the Google Colab where it
Probably,
does.
could you just share your screen if you do not mind? Then I probably can help you.
Sure. Yeah, so that's the on the left. Can you like read it, or is it
Yeah,
too
I
small?
can. Yeah.
Okay. So on the left-hand side is the exercise one. But I can maybe put the. So I mean, it created like the brand new images, but when I tried to use the git clone, and then later on here it said like looks everything good, but then here I get this error that it doesn't find. But also if I look here, I mean there's no directory actually. So I was wondering where within the Google Colab the git clone actually goes.
Yeah. Could you move up a little bit? I think you probably didn't execute one cell a little bit up even more. And then, okay. So looks good. Beautiful soup has worked. Yeah, move down. Okay, this also looks good. And move down. Split folders. And then have you executed training? So the training directory, in principle, you have.
I have like my brand, the train is here, but I also cloned, like I used this command and cloned the git. But then when I try to install it, and I think like that's the issue because I don't actually have split
Could you open it?
folders here. Here, I mean within here, I mean that's the data I uploaded the complete folder, and there's.
Could you move to your Google Colab session, and then you have an icon, the folder, just down. Yeah, this one. And then here.
Here.
Yeah, here you have it.
Copy path.
Yeah.
Got that.
Hope that's gonna work.
No, it gave me again the no such file or directory, but actually.
Yeah, just go to split folders, then you have the 3 dots.
Yeah.
And then copy path.
Yeah, that's what I just did.
That's what you did, yeah. Okay.
Yeah, and I entered it here. I mean, maybe do I need to remove the.
I do not really understand. It actually worked in my case. A little bit difficult. Let me just check it in my case. I mean, in theory, you could also do it by hand, but that's not very convenient.
So anyone else who's using Google Colab, did it all work for you or not?
For me, it worked,
Yes, I use it and it does work for me as well.
but I had a error later.
I'm just trying to understand what could be the problem.
Yeah, I mean, if it works for everyone else, I don't know. It's then it's going
It's
to be
sometimes
even-
good just to restart, your kernel and start from the beginning.
I mean, on the left side, I have a completely other structure than you.
here. Okay.
Yeah, so there, maybe I just download the file again and start and restart it.
Okay. That's
A bit far down. Do we also have to use this history model scratch fit, or is it just for the image generation for the folders?
Let me just, sorry, I'm back.
Sorry.
Well, sorry, what is your question, Antti?
A bit down in the script, here comes the code history equal model scratch fit. Do we
Exactly.
also
So there
to
you're
run
supposed
this, or
there you are supposed to define your own convolutional neural network. Have you?
okay,
Yeah.
okay.
So that's basically you can copy paste and the some of the examples you have earlier in the notebook.
Okay, thanks.
Mhm. So Natalia, are you still here?
Yeah, it still doesn't work.
It still doesn't work. I've tried to check it. So what is happening is basically you have your images in the brand new images folder on your Google Drive. And then you have the output, which should actually bring it to your local Google Colab directory.
Yeah, but it didn't create it. And yeah, I only realized later on when I wasn't able to continue, because then the prediction had like a different size, and then I double checked and it doesn't create those folders.
Yeah. I mean, yeah, it's a little bit difficult. Usually what helps is just delete everything on your Google Colab related with the folder structure and just restart your kernel and try to execute it again. It should work in theory.
Yeah, I'll try to figure it out.
Okay, good luck.
Thanks.
Okay, let me continue just in case you are also executing the cells in part 4 of the convolutional neural network Jupyter Notebook, and you probably have got some first results. So for the celebrity data set, which you also find on Elias, for instance, if I just do the classification with the feature vectors, so I'm basically, if you look here, I'm just generating these feature vectors and then training a very simple model on it, then I get the following learning curve. So as you can see, it's very strong overfitting. So that means should be possible to do a little bit better. So the training accuracy goes almost towards 100%, and the validation accuracy gets stuck at around 55%. But that means probably with some dropout and regularization techniques, you may improve the accuracy. But still, it's interesting to see that you end up with the accuracy of almost 50%, which is not too bad. I mean, there is not a lot of optimization going on here, but that's already first result. Then here, I think it's still training. Yeah, it's a little bit slow. So if you do the fine tuning, that takes a lot of time. But you see here already the validation accuracy is already pretty high. So now we are at around 70%. Okay, okay. That's already done. Okay, very nice. So here the curves look much better. And you see that the validation accuracy is approximately 80%, which is pretty good. Okay, so the comment here is wrong. And then now I think there is some fine tuning going on. What is the problem here? Oh, worked before. What is wrong? Okay, let's just use this Gemini. Tried it before. Let's try whether it works. Doesn't work. really weird because I thought it has worked before, so I'm a little bit surprised. What is the problem here? Okay. So we're testing capacity of Gemini. No idea. Okay, I have to fix it again.
This happens to me all the time.
Okay. But I mean, up to here, so it's only the last part which is causing some issues. Otherwise, should have been. I thought I've checked everything, but okay, I'm gonna fix it. But still, I mean, it's also good exercise and just check the Keras documentation. But I will fix it, so I will make sure that this is gonna run. Anyway, I think it's time to move on. But I think what is nice is if you run it, then at the end, let's just go move here. The very end, there's hopefully the code executed, so you can see how it should look like at the end. Yeah, so that's if you run it in Rancolab, it should work. So in this case, what you see is you will get a confusion matrix for the validation data set. And then you see that, for instance, that Angelina surely gets often confused with Sandra Bullock, which is not very surprising, and also with Catherine Deneuve. So at least if there is some confusion, then it's between women, which is not too bad. And then you also see, for instance, here we have a wrong classification for Sandra Bullock, which was in this case matched to Marion Cotillard, but this is Sandra Bullock. Then again, Marion Cotillard, or some can actually check what was going on, what went wrong. And I think that's always very important if you do image classification, try to understand what is going wrong, especially look at the confusion matrix, look at some concrete examples where you have a misclassification. That's all implemented in here. And I will also fix this thing here in Google Colab, and then you should be able to run it. Good. So basically what the differences were, in the first case, we were simply just extracting feature vectors in the first part of this convolutional network. And then obviously you cannot apply any data augmentation. Then in the next step, we were actually training also the fully connected layers. And there it was possible to use data augmentation. And so we could see that the overfitting issue was already handled much better. So I strongly recommend to go a little to play around with this notebook. I think it's very instructive. But now we have to move on. We still have some material to cover. Good. Okay, and now we are moving from image data to text data. And the reason is that sequence models are best introduced by means of text data. And so there is a particular separate module, which is called computational text language technologies, which I strongly recommend to attend, where obviously you learn in much more detail all these tasks. And I simply want to mention what NLP is about. So basically, you can ask the question, what is the topic of this text? So you can do some text classification. Does this text contain abuse? So content filtering. Does this text sound positive or negative? Sentiment analysis. We will have a look at an example of movie reviews where there is some sentiment analysis. Then the most important part, language modeling. And basically the question is, what should be the next word in this incomplete sentence? That's all about language modeling. That's the main topic of today's afternoon lecture. And then you can obviously do some translation. We will discuss it next week when we introduce sequence-to-sequence models. And then obviously also text summarization. I mean, all these tasks obviously nowadays with ChatGPT and other tools are somehow working astonishingly well, as you all know. But I think it's good to really start with the basic understanding of how these language models work. Good. So since we are now moving to text data, it's important to also think about how you prepare your text data in order to feed them into neural networks. And obviously you cannot feed words into neural networks. So what you need to do is you need to process this text data. So the first step usually consists of standardization. That means you, for instance, you are using lowercase, you're removing punctuation. There are some other standardization techniques such as lemmatization and so on. Then you decompose this text into tokens or in the smallest units you're wishing for. Obviously, you could also decompose it into letters, but here we are going to decompose it into tokens. And as a separator, we consider white space. Then you need to index all the words. So you assign integers to your tokens. And then in a last step, what you may do is some one-hot encoding or embedding. So let's first start with the one-hot encoding. Let's say you have 20,000 tokens. Then in theory, you are going to end up with vectors of length 20,000. So you're going to have 20,000 entries. And then if you have the word cat, you may say this is actually referring to position 4, or position 4 is referring to the word cat. So whenever you have a 1 position 4, then you know there is the word cat in your sentence. Now what happens is that one-hot encoded word vectors are highly dimensional. These are high-dimensional vectors. So basically, if you have a vocabulary of 20,000 different words, you are ending up with vectors of length 20,000. And obviously, they are extremely sparse, so mostly consisting of zeros and only some few ones. And it's really some hard-coded vectors. Now, what is done is you want to go for a more dense vectors. So what you're doing is you're using so-called word embeddings. They are lower dimensional and they are learned from the data. And what is nice is in some cases they may even there is some geometric interpretation. So for instance, words which have a similar meaning are in the embedding space next to each other or near to each other. And what is also interesting, you can do even some arithmetic. For instance, you can subtract man from king and then add woman, and then you are going to end up with queen, or this is the wild animal, and this is the domesticated animal. So if you move down here from wolf to along this direction, then you end up with dog. And you could do the same arithmetic with if you have tiger, you can move down into the same direction, and then you will get cat. So that's the geometric interpretation of word embeddings. And in order to get a little bit familiar with text data, I recommend to study this Jupyter Notebook part 1.1. And so now we are moving to the new folder, which is language models and recurrent neural networks. So just, and it's also supposed that you are using it in Google Colab. So there I really have tested everything, it should work. And that's basically what you have seen. And so now what we can do is there is this Keras layer, which is called text vectorization. And for instance, what you could do is you can define a text vectorization layer, which is outputting some integer values. What you will find here is, for instance, you can have this data set, then you can adapt this text vectorization layer to this data set, which consists of 3 sentences. And then you may get the vocabulary. So this is the out of vocabulary token. And then usually they are ordered with respect to the frequency. So those words showing up on the top are the most frequent ones. Okay, now let's move to this movie review data set, which consists of 25,000 training sentences and 25,000 validation or test sentences. And you have 12,500 text files which have a positive or which are expressing some positive sentiment. And you have 12,500 text files which are expressing negative sentiments. So for instance, here you have one text. I first saw this is one movie review. I first saw this back in the early 90s, blah, blah. And then you have best viewing is at night, very few parts. Then you can also see whether it's positive or negative. Yeah, so it basically has 2 categories. And then we split everything in the following ways. So we get 20,000 files, which belong to 2 classes, 5,000 validation files, and 25,000 test files. So again, here we have movie review. This was the worst movie. That's going to be probably negative sentiment. So you can execute it, and then you can actually see how you can do some classification based on single words. So this is the bag of words classification. Let me just explain how it works. So the bag of words classification works as follows. So basically you are creating one hot encoded vectors of length 20,000. And you're simply considering or looking at whether certain words are showing up in a movie review. So you get ones in case a token is showing up and zeros otherwise. Then you're feeding in these one hard encoded vectors to a fully connected layer with 16 hidden units. And then you have a dropout layer. And then at the end, this is a binary classification. So you remember the last layer activation should be a sigmoid activation function. You have the RMS prop optimizer. And then you can fit the model, and you see you're going to end up with validation accuracy of 94%, which is pretty good. Or yeah, test accuracy of 88.7%. So that's the data set, and I would like to give you 10 minutes just to go through it, try to think a little bit about what is happening. I think it's try to run it on Google Colab. Just use this notebook on Google Colab. Okay, welcome back. If you could shortly confirm that you can see my slides and hear my voice.
Yes, yes.
Wonderful, thanks. Okay, so now we have moved to text data, and you have this data set, the IMDb movie review data set. And here we have introduced this Keras layer text vectorization. So what you can do is you can actually define some settings, what you're going to output. You can output one hot encoded vectors. Then you have some default standardization like lowercase letters, removing of any punctuation. And this is going to be obviously what you're going to feed into a neural network. We have seen this bag of words approach. Basically, you simply have your movie review, and then you have, let's say, a 20,000 long vector. And whenever you have a 1, that means you have the corresponding word. If not, you have a 0. There are some other encodings, such as the term frequency and inverse document frequency. So obviously, you may try to understand how important the word is, so how often it shows up and how important it is. And this is this term frequency, inverse document frequency encoding. So if you attend the course Computational Language Technologies, you will learn about this encoding. But you also have a section in the Jupyter Notebook, part 1.1, where this encoding is applied. Good. Now, this is now a starting point to introduce sequence models. And let me first remember what the vanilla neural network is. That's the fully connected neural network we have discussed in block 2. So basically what you have is you have an input image in general, then you have some hidden layers, and then you have some output, which is going to be a class distribution over distribution of probabilities over different classes, for instance, or just at the end a simple class. Now, sometimes things are a little bit more complicated. So let's say you want to describe what is going on in an image. That's referred to as image captioning, and we will discuss how it can be done next week. So in this case, we have an image, and then we are feeding in an image into a neural network. And the idea is that we are going to get a sequence of words which is describing what is going on in the image. So obviously in this case, with the fully connected neural network, it doesn't work because here you have one image and you have a varying length of the sequence. So depending on the image you're feeding in, you will get a different sequence and obviously also different sequence length. So the fully connected neural network structure is certainly not appropriate to do this task. Then sentiment classification. So for instance, here we have movie reviews, we have sequence of words, and we want to express what is the sentiment. Is it a positive or negative movie review? And obviously you have different length of your movie reviews, so it's not that they always have the same length. So you need a more flexible architecture which is dealing with this kind of situation. And then we have the situation, for instance, where we translate, for instance, a sequence of words in English to sequence of words in French. And again, here, the sequence of words in French may not be the same length as the sequence of words in English. So again, what we need is a more flexible architecture. Or for instance, video classification on frame level. So for each frame, you want to say what is going on in this frame, what kind of activity is happening. And again here, for each frame, you will have one output. So again, that's something which is not going to be solved with our convolutional, either fully connected neural network or convolutional neural network. And in order to fulfill these tasks, which were described here, we introduce so-called recurrent neural networks. And we will introduce these recurrent neural networks by means of language models. So language modeling is actually the task of predicting what word comes next. So if we have the sentence the students open there, we have different options. And language modeling is about predicting what is the next word. In this case, you may get a probability for each of these words. That's exactly what is expressed here. So you have a sequence of words, the students open there, and then it's about predicting the next word. So given a sequence of words, what is the probability of the next word being books or laptops or exams or minds? So the next word can be any word in the vocabulary. Let's say, let's denote the vocabulary with capital V, and the number of words or the size of the vocabulary is these absolute signs of V. Now, what you can do is you can also think of a language model which is assigning probability to a piece of text. And the reason is, let's say this is a sequence of words, so that's some text, let's say a movie review, and the probability that this sequence of words is showing up can be written as a product of conditional probabilities. So for instance, here we have a sequence of words. Given a sequence of words, what is the probability of the next word? And so yeah, you can decompose this joint probability distribution as a product of conditional probabilities. And each expression here is actually what a language model is providing. So for each expression here, basically that's exactly what your language modeling is doing. It's predicting the next word given a sequence of words. Good. So, well, this was, that's already a little bit, yeah, obvious. It has become obvious what our language model is doing. Well, I think most of us are using tools like ChatGPT on a daily level, but it's also showing up if you're, for instance, writing a text message and make some proposals, what is the next word. It is also if you're Googling, then you get some propositions, what are you actually looking for. And let's try to set up a model which is solving this task of predicting the next word. Let's say we have the word, the sequence of words as the proctor started the clock, the students opened there. Now we will first go for what we know best. We know fully connected neural networks. So let's try to solve this task of predicting the next word by means of fully connected neural networks. So you know, for a fully connected neural network, you need input vectors of identical length. So what you need to do is you need to fix a window size. In this case, you may say, okay, you only can consider the last 4 words before the word you want to predict. So that's a fixed window size. Let's assume here the window size is 4. Sorry, it's the wrong direction. So in this case, what you can do is you can have the students open there. Each word is represented by means of a one-hot encoded vector. Again, let's say you have a vector of length 20,000. Then each position refers to a word. If the word is showing up, then you get at the corresponding position a 1, otherwise zeros. To get a lower dimensional representation of these words, we use word embeddings. So you can then think of a lower dimensional space. Usually these are vectors of length 556 or 256 or 512. And then you can concatenate these word embeddings. You get some fixed length vectors. And then you can apply some matrix multiplication. You can add a bias and then apply an activation function. So this is going to be your first hidden layer. And then you may have another matrix multiplication, adding some second bias vector. And then you apply this softmax function, which is going to result in a distribution, in a probability distribution over words. And in this case, books or laptops would be the most probable next words. Okay, that's the way how you could do language modeling, predicting the next word. But there are some problems with this approach. So first, usually fixed windows are too small. So if you want to summarize an entire book, well, you will be in trouble if you are going for the fixed window approach, because it's going to be simply too large, and then the weights are simply going to explode. You're going to have way too many parameters. But windows never can be large enough, so that's also an issue. Good. Now let's introduce a new network architecture which was trying to solve this issue of the fixed window size approach for language modeling task. Let's say we have a sequence of words, and in this case, it can be a sequence of any length. And what we are doing is this is the input at position 1. This is the input at position 2. And we will create so-called hidden states. So what you do is you produce some hidden states, and hidden states actually depends only on the previous hidden state and on the input at the corresponding position. So the idea is that you are going to apply the same weights repeatedly, and this will become a little bit more clear if we look at this explanation here. So what you usually do is you start with an initial hidden state. This can be you can actually consider it as a random vector of size, whatever you want. Usually don't choose it too large. And then you have your sequence of words. The students open there. So you have 4 words. You have the one-hot encoded vectors for each word. And then what you're going to do is you're going to apply this word embedding. You can think about the matrix multiplication, which is projecting your one-hot encoded vectors onto a lower dimensional space. And then what you so this is the input. This is the word embedding for your first word. This is the word embedding for the second word. And then the goal is to compute the hidden states. And the hidden state is actually obtained on the basis of the previous hidden state and on the actual input. So here you have a matrix for the previous hidden state. So you applied this matrix, these weights to the previous hidden state. You get this matrix multiplication of WH with the hidden state of the previous hidden state. Then you have the matrix multiplication WE with the actual embedding vector, and then you are adding a bias vector. So this is going to result in this hidden state. Yeah, obviously you have also to apply some activation function. And now it's a little bit surprising, but here you're still using 10H. We actually came to the conclusion 2 weeks ago that we shouldn't use 10H, but in this case it's still used. Okay, and then you have this hidden state, which is then going to be used to compute the next hidden state. And you can think about these hidden state cells as some information which is flowing through this sequence. So you are keeping some past information and updating the information based on the actual input. Then at the last step, you take the last hidden state, you apply again a matrix. You again have a matrix multiplication, which is applied to the last hidden state. You add a bias vector, and you obtain a distribution over words. And then if you apply softmax function, that means that you will end up with a distribution over a probability distribution over your vocabulary. So let's say here you have 20,000 words, and you get a distribution over all these words of your vocabulary. Good. So the advantage is that if you have this architecture, in theory, you can process any length input. So your input could be theoretically of any length. It's not going to affect anything because the weights are the same. They are not increasing in size if you have a longer sequence. So that's not a problem. Then in theory, you can also use a lot of information from many steps back, and the model size doesn't increase. So that's what I already have said. The problem is that this is a pretty slow method because you cannot parallelize this process. So you have to compute the gradient, which is flowing through the entire sequence of hidden states. So you cannot somehow speed up this process. And as we will discuss in a second, in practice, it's actually difficult to access information many steps back. Okay, let's think about how we can train this model, this recurrent neural network language model. So first of all, you have to think about, we have a big corpus of text, which is a sequence of words. And in this case, you already have the ground truth because you want to predict the next word and you know what the next word is. So that's the huge advantage of text data. You basically always have the next word, the ground truth for the next word. And this makes obviously training much easier, and it's reliable as long as you have grammatically correct sentences and meaningful sentences, then you have your ground truth. Good. So what we are doing is we are the language model based on recurrent neural networks is predicting or computing the distribution over the vocabulary for the next time step. So you get the probability distribution for every word, for every next word. And that's obviously very convenient to compute the cross-entropy function, because basically you can just compute the logarithm of the probability for of the next word, which is actually which is the true next word. So I think it's the easiest to show it here. So let's say here you will end up with the probability distribution. So that's a probability distribution over the entire vocabulary. And then all you need to do is you need to pick the probability for students, because you know the next word is students. So all you need to do is you need to pick the probability for students and then compute the negative logarithm of this probability. And then at the end, what you're going to do is you're going to add up all these loss functions at each time step and take the average. So you get at each step, you get a loss function, which is always minus the logarithm of the probability for the next word. So here you already know what the next word is. It's open, and your model is going to output some probability for the next word being opened. So you can compute the negative logarithm of this probability. Then at the end, you can average all these loss function values, and that's going to be your total loss.
Sorry, one question.
Mm-hmm.
At the hidden state 0,
Mm-hmm.
with which values does it start there?
Yeah, a very good question. Thank you very much. That's so you have two choices. Either you're going to initialize them randomly, so you just have some random initialization, or you can also try to learn these as parameters. You may say, okay, that's kind of a parameters of the model, which we also have to learn. So there are these two ways. Good. Okay, now just remember if in stochastic gradient descent, you are never considering the entire data set. So if you have an entire book, you're not going to consider the entire all the words, all the sentences. You're always taking a batch or a subsample of the data, and the same is going to happen here. You are simply considering a subset of the entire sequence, because otherwise it's going to be too expensive if you're going to compute the loss function over the entire over the entire sequence of words. Now there is in theory, we said you can access all the information from as many steps back as you want. But in practice, there is this so-called vanishing gradient problem. So the more steps you go back, the smaller the gradient becomes. So it's vanishing. It's getting always smaller. And obviously, if the gradient is getting towards 0, you are not anymore learning from this hidden state or from this information. So that's one problem. And yeah, so the gradient can be viewed as a measure of the effect of the past on the future. So if the gradient is vanishing, then the effect of some time step on the future is going to become very small. So here just an example. let's say we have the sentence, when she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her, and for us it's obvious, tickets, right? But for a language model, it's not that easy, because here the word tickets showed up at position 7, and now probably 30 positions later, I didn't count the number of words. You have to understand that the next word here would be tickets, which lies back quite a lot. So this is actually a problem if you have a vanishing gradient, because then here the gradient, which is taking into account the word tickets at this position, may be so small that it's not going to be of any relevance at this point. And that means that you will predict the wrong next word. And just to make it clear, you have this language modeling task. So the writer of the books is or are. And we distinguish between syntactic recency. So in this case, the writer of the book is. So you understand what the syntax is, and that's going to yield the correct next word, which is obviously is. But often recurrent neural networks are actually better at learning from sequential recency. That means they are just looking at the most recent word, and this one is in plural, so it's going to be also, it's going to choose accordingly the verb in plural. Okay, so this is a serious problem. So the theory was nice and beautiful. So it was this recurrent neural network, which in theory should have worked for any sequence length, but in practice, it's not doing so. So what we have are long short-term memories, and that's one of the very famous architectures. It's still one of the most cited papers in deep learning, and it was proposed by Hochreiter and Schmidhuber in 1997. So this happened actually in Switzerland. It's not everything happening in Stanford, Silicon Valley, or MIT, but this happened in Ticino. So they proposed this architecture in 1997, and it was not that popular in the 90s and 2000 years, but it became really popular in 2011. We'll come back to it. And the idea is they try to solve this vanishing gradient problem by introducing a so-called cell state, which is supposed to store long-term information. So that's the reason it's called long-term and short-term. There is still a hidden state, which is somehow digesting information coming from at the given time step. And then there is this cell state, which is, as I already said, storing long-term information. So it's a rather technical architecture. I will go through it. And this is the recurrent neural network, which we have discussed before. So we have some input, and then we have the hidden state, and, or we have some embedding vector layers, whatever. And then as an output, you have a hidden state. And then this hidden state is going to be used to compute the next hidden state. Now, the long short-term memory LSTM network is working at two levels. So on the one hand, we have the hidden states, and then on the other hand, we have the cell states. So this is the cell state level, and then we have the hidden state. And yeah, let me I don't want to go too much into the details of this architecture. It's all kind of, you can read it up in the lecture notes, or it's getting even clearer if you spend some time on these illustrations. But yeah, well, how does it work? So first of all, you have so-called gates. This is a forget gate, and gates can be open or closed. So they are deciding whether something should be memorized or forgotten. So in this case, you're concatenating the previous hidden state with the current input. You're applying a weight matrix for this gate and adding some bias activation function. And then you have a gate which is deciding whether you are going to keep some information or not. Then you have the input gate. It's always the same philosophy. You're concatenating the previous hidden state with the input, the current input, applying some weight matrix and adding some bias vector, applying again some activation function. And then what you can do is, by means of this, you can also compute some transitory cell state. So that's again, you're using the concatenated hidden state and input vector, applying some other weight matrix, adding some other bias vector, and here applying a 10H activation function. Good. And now you see what happens is, based on these two gates, we have the forget gate and then we have the input gate. You will decide what is becoming the cell state for the current position. So you apply the forget gate to the previous cell state, and then you add the input gate applied to the transitory cell state. And then you have an output gate. So this is an output gate, and again, here it's always the same idea. You concatenate your hidden state, the previous hidden state, with the current input. Then you apply some weight matrix, you add some bias vector, and you have here an activation function. And then in order to get the current hidden state, you simply apply the output gate to 10H of the current cell state. So that's the way how you compute all this. That's the summary, or this is another summary. So basically you have three gates: the forget gate, the input gate, and the output gate. So these are sigmoid functions. We get values between 0 and 1. And they decide how much information is forgotten, how much information is used as an input for a transitory cell state. And then we have the output gate. And here we have some new cell content or some transitory cell state, which is going to be computed as follows. And then the final cell state at time t is going to be computed based on the previous cell state, where the forget gate is going to decide how much should be forgotten. Well, if you have 0 here, then no information is kept from the previous cell state. If it's 1, then you keep all the information from the previous cell state. Then we have the input state, which is going to be applied to the transitory or new cell content. And then the hidden state can be computed based on the output gate. So it's super technical, but it works quite well. And then you have a little bit an alternative, which was proposed in 2014, the gated recurrent units. So what you have here, again, you have a update, you have two gates. It's a little bit simpler. You have a update gate and you have a reset gate, and then you do not have any cell state, but you have some transitory hidden state where you applied especially the update gate here. So this is a little bit easier without cell states. And well, what are the differences? So researchers have proposed many gated recurrent neural networks. There is an entire zoo of recurrent neural network architectures, but if you check the literature or nowadays what is used, LSTM and GRUs are the most widely used ones. And as a rule of thumb, LSTMs are a good default choice, and GRUs are especially propagative speed and parameter space is an issue. So now just what is very important is LSTMs were in the beginning used really Google when you were actually trying as a language model. So if you were typing some request in Google, then LSTMs were used. But still in 2017, this was the architecture which was used by Google as a language model. Or 2016, this was still when transformer models slowly popped up. Nowadays, these two architectures are mainly relevant for time series analysis, and that's the reason the exercises I have included for this block are mostly dealing for time series data. And there, LSTM and GRUs are still super relevant. You're always trying an LSTM models whenever you are doing some time series analysis. So these two architectures are still relevant. Obviously, nowadays you are also working with transformer models if you are doing time series analysis. But often that was my experience. GRU models outperform quite often transformer models for time series data. Good. Yeah, so it's just as a side remark, it's LSTMs do not completely solve the vanishing gradient problems. It's you wouldn't really use recurrent neural networks for any task, whether it is language modeling or time series analysis. But LSTMs are much better, but still it's not that you have a guarantee that there is no vanishing or exploding gradient. So that's just as a side remark. And yeah, between 2013 and 2015, this was really a world success. This was one of the most important architectures. And obviously in 2017, there was this famous paper, All You Need is Attention. We'll discuss it next week. Well, they were basically completely replaced by transformers. However, recently, Hochreiter, one of the authors of LSTM, he recently came up with somehow a new version of LSTM, and he pretends it's doing as well as transformers. Whatever. It's not anymore that widely used. Still, for time series analysis, I would say it's still highly relevant. Good. Now, if you're working with recurrent neural networks, or yeah, probably let's have a break. I think it was a longer session. Let's have a break, and then I will say a couple of words. Let's make a break of 13 minutes. Is this fine? Let's continue at 55. But if you have questions, please just ask. All others can go for a break. I'm going to be here for 2-3 more minutes.
As optimizer, we use RM as prop or RNN, or
again, it's always problem dependent. I would say usually a good default optimizer is Atom. RMS prop is also doing pretty well. To be honest, I mean, my experience is first, you really try to come up with a good architecture. You try to really understand what are the issues of your data. It's better to spend time on these issues and to really proper data pre-processing and before you start thinking too much about the optimizer. But obviously, it's always good to, if for instance, what happens is if you look at TensorBoard and then you see that there, for some reason, your network is not learning. So you see that your weights are always the same. They do not get adapted. Well, then in this case, you may exchange your optimizer. But it's not something you would think too much in the beginning.
okay, I was just wondering because in your code you're using it, and prior we had Atom as default because it performed the best. So I was just wondering.
Yeah, usually I think Atom is doing great job. So I would always start with Atom, and I mean in Keras it's also the default optimizer. So I think it's a very good choice.
Okay, thanks.
Well, then let us continue. As usual, if you could shortly confirm that you can see my slides and hear my voice, that would be appreciated. Are you still with me?
We do both, yeah. We hear you and see you.
Okay, wonderful. Thank you. Good. Now, let's somehow define some 2-3 very, very important technical aspects how to apply and implement recurrent neural networks. So let's have a look at the following sentence. The movie was terribly exciting. Now, the problem is, how are you going to represent this word terribly? Well, if you are going to read it from the left, then you would probably conclude that the word is rather negative. It would have a rather negative connotation, right? However, if you would read it from the right, then you would see the word exciting, and in this case, the meaning of terribly would change from negative to positive. So one way how to cope with this situation is that you have, on the one hand, a forward recurrent neural network where you're actually proceeding from left to the right. And then you have a second recurrent neural network, which is proceeding from right to the left. And what you are doing is, at the end, for the hidden state, you are simply gonna, you will get concatenated hidden states, and which somehow will get a more accurate representation of the word terribly in this case. So in this here, the red units would be probably rather negative connotation, whereas here you would get a better representation, which is somehow representing more the context. Good. So that's one way how to get better contextual information by using so-called bidirectional recurrent neural networks. So basically you have one forward recurrent neural network, one backward recurrent neural network, and the second layer of hidden states will be the concatenated hidden states of these two. Good. So this is a general, basically you can have here the forward recurrent neural network, FW, and then you have the backward recurrent neural network. Then you're going to concatenate the two hidden states, and this is going to be the hidden state of the bidirectional recurrent neural network. And this is actually what we will pass on to the next parts of the network. Good. And generalization of these bidirectional recurrent neural networks are so-called multi-layer recurrent neural networks. That's the way how to go deep with recurrent neural network. That means we are not only considering one recurrent neural network, but actually several ones, and stack them on top of each other. So that's going to look like as follows. So basically you have here the sequence of words, then you have your first recurrent neural network layer, and now for the second recurrent neural network layer, instead of using the embedding vector of the word of the input, you're simply going to use the hidden state of the first recurrent neural network layer. And you can, in principle, you can stack different recurrent neural neural network layers on top of each other. So what are some best practices? Usually we have multi-layer recurrent neural networks, but we are not going to go as deep as in the case of convolutional neural networks or feed-forward networks. In 2017, one of the state-of-the-art methods for neural machine translation used 2 to 4 layers, and this was actually the best performing model. Exactly. So what you can say is often 2 layers are much better than 1 layer. 3 are a little bit better than 2. 4 is not anymore that clear. And then what we are also applying are so-called skip connections. That's what you have seen in the ResNet last week. That's something which is super important. We'll discuss it next week, these skip connections. And we will see transformer-based networks are much deeper. They are usually using 12 up to 24 layers. That's going to be the topic of next week. Good. Let's have a short look at how these bidirectional networks are implemented in Keras. Good. Let's go a little bit down. So we are still in the example for the IMDb movie review data set. So again, here you see bidirectional recurrent neural networks, in particular bidirectional LSTMs were considered to be the state of the art for sequence modeling. So still, it's not that long time ago, 7 years around, and these bidirectional recurrent neural networks were state of the art. So nowadays, obviously, if you have sequence modeling, it's always done with transformers. I said it's a little bit different for time series analysis. There, you would still first give a try to LSTM or GRU models. Often they are outperforming transformer models. Good. So how do you implement such a model? Basically, you have here your embedding layer. Then you have a bidirectional LSTM layer. So you use layers bidirectional, and then you have a LSTM layer. So that means as an input, you have the embedding vector, and then you have 2 layers, one going into the opposite direction. And then at the end, you have dropout. So you're going to use the last stacked or concatenated hidden state, apply a dropout layer, and then you will use this as a classifier. Then you have a fully connected layer first. You get a 1 output sigmoid last layer activation function and binary cross entropy loss function. That's one way how to do it. Here you see how things work. And go down, and there is another way how to do it. Well, it's almost the same. What is the difference here? Yeah, here we also have an embedding layer. So here we are also learning an embedding layer. Otherwise, the architecture here is the same. Good. Well, let's go back to the slides. Good. Now, oops, was not purpose. Now, let's see how we can use these recurrent neural networks, in particular LSTM network, and we are also going to use a multi-layer LSTM network to generate text. Again, this is not anymore relevant because we generate text with transformers. Nevertheless, I think it's a good way to really understand how language modeling works. So let's say we have a sentence, my favorite season is. Now we want to predict the next word. And what we are doing is we're using a sequence model. So first we have our embedding vector, then we have the initial hidden state, and then we are computing the actual current hidden state on the basis of the previous hidden state and the current input embedding vector. And then we have this hidden state, which is then like information flowing through the sequence and taking up all new relevant information and keeping older information. Here, obviously, what we can do is at the last layer, we can predict the next word. And then this is going to turn into the following sequence. My favorite season is spring. Well, and now we could simply continue. We can use spring as the new current input, compute the embedding vector, and we get a new next word proposition. Then you choose one next word, and this may continue like that for a while. And so that's going to be the part 2 of this Jupyter notebook. Which is going to be a little bit fun. I hope so. Yeah. So what you can do is the following. You can go to the Gutenberg site. So here you can choose any book. Let's say you want to have this book here. Then you go to the this is where is the, then you go to plain text UTF and you have the entire book here. That's perfect. So you can simply copy paste the link to this website, and then what you can do is so basically just copy paste your book you want to choose in here. And then I have chosen Goethe's Faust. And so here you can see the beginning of Goethe's Faust 1. Mögt ihr walten, wie aus Dunst und Nebel um mich steigt, mein Busen fühlt sich jugendlich erschüttert, vom Zauberhauch, der euren Zug umwittert und so weiter. Then we can clean the text here. It's done a little bit in a different way, not with the text vectorization layer, but a little bit more in a way using some Python functions. But I think it's also good to see this kind of this way of cleaning data. Then we have the tokens, so we can we get all the tokens from the book. Ihr naht euch wieder schwankende Gestalten, die für sich einst im trüben Blick gezeigt. You see it's, we have applied all this cleaning, so we have lowercase, we have removed punctuation. It's basically all this kind of cleaning. That's the result. And then you can have a look, and we see that in total in Faust 1, there are 30,600 tokens and 7,000 unique tokens. And then what we are doing is basically we are saving, we have always sequences of length 50, and then we are shifting by one step. So here we have ihr naht euch wieder schwankende Gestalten, then the next sequence is naht euch wieder schwankende Gestalten. So we have removed this word and moved one step to the right. And the reason is that we are going to use obviously this this structure, these sequences in order for the language modeling. And now let's have a look at the language model. So here we are getting integers for each token. It's a little bit long, 7,000 unique words. Good. And then I want to move to...
Is this integers like simply numbers?
Yes, absolutely. Yeah, sorry. I was a little bit fast. So you have for each word, you have an integer. And this is kind of a dictionary, right? So basically you have the key and then you have the value. And yeah, so you're going to, in the next step is then you can use this number for one-hot encoding. So that means we will have vectors of length 7,005. And then if you have the word Gregory, okay, now obviously I have, this is weird. I think here I have used a different, I have used a different book. Anyway, it doesn't matter. Then I will get a 1 at position 6,867, right? So that will be useful for one-hot encoding. And then again here, this is a sequence of words with the corresponding token integers. And now let's have a look at the model. So first of all, we have an embedding layer. So we are learning the word embedding here. And then we have a first LSTM layer with 100 hidden units. And at each time position, we are actually returning this LSTM hidden layer. So at each time point, we hand over this hidden state to the upper laying LSTM layer. And here we only, for the top LSTM layer, we are only considering the last hidden state. And here we are going to apply a fully connected network with 100 hidden states and the rectifier linear unit. And then from this hidden layer with 100 hidden units, we are going to generate a probability distribution over the entire vocabulary. So we have for 7,005 words, we get a probability through this softmax layer. And this is going to be used to generate the next word. And yeah, let's then you can move on. And so here we are learning this multi-layer recurrent neural network. That's all good, all good, all good. And then we want to generate the text. That means here I start with a seed text. So Welt ist gar so weit. So this is I just take out one sequence consisting of 50 words. And now you can generate the next word, and then you move one to the right. And you do this for a number of times, and then you can generate the new text. And this is the generated text. So mit gewaltig, wodurch Köhe und meinem Fenster gebannt, deinen Schale, wie sie erbärmlich jeder Geist in der Stille stieg der zum Berg einst Gunst Faust. Okay, so this is the text which has been generated. And if you read it, it doesn't make sense at all. Grammatically, it's okay. I also have to say I was training it for 2 hours. I was only training Goethe's Faust 1. But just to let you know, I mean, up to, I think 4 years ago, this was still, I wouldn't say the best you could get for language modeling, but it was you could generate text, which was grammatically more or less okay. And so just to be aware of this really incredible surprise, what happened in the last 3-4 years. I think it's a huge step forward, and I think many people were really surprised because I mean, I've been using this kind of example for now almost 5 years, or yeah, 5 years. And in the beginning, it was okay. It was obviously you could do much better if you train longer, if you take more text to train your LSTM. But I mean, it was just incredible when these large language models showed up. This was a huge, yeah, I mean, I think most people were surprised. But okay, now obviously this is not any more relevant for language modeling, but I think it's very important to understand how these recurrent neural networks work. And in the exercises you have recurrent neural networks for time series analysis, and I think there it's still highly relevant. If you run some time series analysis, then you will still train an LSTM or GRU network just as to see how it is performing, and often it's surprisingly well performing. But anyway, you can choose any book you want. You start training your model after 2 hours. You can start generate text, which was trained on your favorite book. Good. Are there any questions?
Yes, I got one. Could you maybe specify some use case for using LSTM for time series analysis?
Yeah, we can go directly to the exercises. So I really strongly recommend to solve these exercises. So you shouldn't go directly to the solutions as I'm doing now. But so what we have here is this Jena data set, which is about predicting the temperature. And what you have is basically you have, that's the data set. So you have a lot of information like pressure, then some other atmospheric values. So in total, you have 14 weather-related values. And now the idea was, and you have it's a large data set, so you have 420,000 lines or time points. And now the idea is, can you actually predict the weather of the next day, given all the information you have? Given all the other information. So basically, what is given is you have pressure, then you have these other values. Can you predict the temperature of the next day? So that's how it looks like, this data set. That's an outline. Then, well, the question is, can we predict the temperature even in 24 hours so that you make a prediction for the next day? That's what I said, yeah. And yeah, that's it. So I strongly recommend go through this through these exercises. It's really relevant, and it's also what you're going to do is you have some LSTM models or GRU models. So you're trying out different models. First, we'll just go for a fully connected neural network and so on and so forth. Does this answer your question?
Yes, thank you.
Okay, very good. So also relevant information, you also have now a mock exam on Ilias. So this already allows you to get some idea what could be asked at the final exam. At the exam, you will have a part where you have to do some small computation like we did for the quizzes, and then you will have a part where you have to code, but very basic coding. It's really a keras, so you have to be able to manipulate keras code. Good. Any further questions? I'm going to be here for 5 more minutes or even longer if you have some questions. Well, I think next week we will finally discuss sequence-to-sequence models, attention, and then transformer models. Unfortunately, we won't have a 7th lecture where I would have introduced graph neural networks, which are really beautiful. It's kind of a theory of everything, which would encompass all the other network architectures. But yeah, probably can think about the evening session, or you simply go through the material yourself. Good. Any questions? If not, I'm going to be here for 5 more minutes. Just can also ask questions afterwards. Otherwise, have a very good week. See you next week, and all the best.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.
For the exam, will we use Google Colab or Rancolab, or does it not matter? Or
it doesn't matter. What I do is I really check that everything is going to run on Google Colab and on Rancolab. So if I give you some model which you are supposed to run, I prepare everything so that you can read in the data and some already edited code, which you then simply have to complete. And there I will check really carefully that it's going to run on the even 1 day before the examination, that it's also going to run on Google Colab. So to make sure that if 2 days before there is some change in Google Colab, that it's still going to run. You are also free to run it on your own laptop, but there I cannot give any support if you run into problems.
yeah, no, I was just wondering, since I had like those issues with Google Colab that no one else seemed to have, I was wondering if it would make sense to like get Rancolab also working for me.
What I recommend is, I mean, sometimes it's really, if you are working with Jupyter notebooks, is you are probably skipping one cell, or you it's really for Jupyter notebooks, you have to go through linearly, really from the beginning to the end. It's very unlikely that you will get such an issue. I think just try to do it again. The only thing what I have observed, do you have a Google Pro license, or what do you have?
I'm not sure, to be honest. I don't